All right, good evening, everyone. Okay, so tonight I'm going to go on with Module 2. I think we got to, at this point where we spoke about about signal conditioning and why it's necessary. And I believe we also looked at some points in the textbook as well on this and on some of the other things that we haven't really seen in the slides yet. But in any case, I am going to continue with the circuits now, and I think best way to kind of demonstrate this, I think we can do maybe an example if the textbook does provide any, you call it, exercises on these circuits. We can do them as examples in class. I think might not be a bad idea to look at that. Right, I probably just need to make the slides downloadable for you guys as well. Hopefully we can also move on to Module 3, which will be on ultrasonics and radioactivity. I am, however, so there's been quite a bit of change on the syllabus in terms of those two components that I haven't worked into the slides yet. So something that used to be part of Module, what is now Module 4, which used to be Module 5, more destructive testing and inspection, that your different methods of ultrasonic testing on materials is now being done within Module 3. And the same thing goes for X-rays, doing flaw detection or fault finding with X-rays on materials, also done now in Chapter 3 instead of Chapter 5. Right, but in any case, let's continue with Chapter 2. Just going to make this downloadable real quick. All right, so so the first circuit that we have here is the essentially a non-inverting amplifier, or what it would be referred to in the textbook as a multiplier, which is essentially just a straightforward amplifier circuit. So if you have a very small signal that your transducer is picking up and you want to analyze that signal further, you're going to need some amplification. So then you would generally use something like a non-inverting amplifier. You can also use an inverting amplifier, but generally non-inverting amplifiers are used. Right, and while we're here, I'll sort of do two examples on this as well. All right, then we have the detector bridge. Now, what is not shown here very nicely, or I feel like with the drawing that I have here in the slide, it's not very explicitly shown, is that we are measuring the voltage between these 2 points, right? So usually this goes off to some amplifier, usually a differential amplifier, so amplifier that will basically amplify the difference between these 2 points. So let's say under normal conditions, we select this bridge so that the bridge is balanced. So basically what that means is that your value there of your, in this case, a thermistor, is the same as all the resistors. So if this is, let's say we are at our room temperature here, and that's 1 kilo ohms, then it's easier to just select all the other resistors as 1 kilo ohms. Now, essentially what will happen is if you have any variation, so if you have any change there on your thermistor, basically what it's going to do is it's going to change the value of the voltage at this point, because now the voltage drop across the thermistor is now going to be different from the voltage drop across R2 there. So now you have a difference in voltage that you can amplify. And you guys can see actually in the formula for the output voltage across the bridge, that's essentially what you're going to have here. Now, you guys also notice that there's no difference in voltage. So if all the resistors are the same size, the difference here is going to equate to 0, right? So this portion and this portion is going to be the same. So thus 0 difference in voltage. Right, so I do have an example here already in the slides of how we can, or how a detector bridge actually works. So yeah, so we have, let's say, a detector bridge with 3 standard resistors, 1 kilo ohm each. And then we have a resistance thermometer or a thermistor or whatever, and that has a nominal resistance of 1 kilo ohms at 20 degrees C. So essentially what you're going to do is in practice is that you're going to build this circuit maybe at 20 degrees C or an environment where you have 20 degrees C, just so that your bridge is balanced, and you make sure sometimes you will have some of the other resistors will be adjustable, just so that you can get a balanced bridge under, let's say your normal conditions would be 20 degrees C, and then you would go place your thermistor wherever you want to measure the temperature, and then have your leads come out of whatever thing you're measuring in, and yeah, and that will then essentially be your environment that you're measuring in, then connected to a circuit. So yeah, so so that's essentially in practice what you would do, and then you would have your detector bridge basically on those 2 points that will then be connected to a difference amplifier, right? Okay, so we're further given the temperature coefficient of the thermometer or resistance thermometer as 0. Actually, that unit is not correct. It should just be 0.001 per degree C. And we are also given a supply voltage for the bridge as 3 volts. Right, so if I can quickly just go back to the drawing here. So the supply voltage here we have as 3 volts. In fact, I chose the values actually quite nicely here. So that 1 kilo ohms there is at 20 degrees C. So something that you guys need to keep in mind there. All right, so the first thing that we're asked here is to calculate the voltage across the detector or across the detector bridge when the temperature is 100 degrees C. So we actually need to go calculate what the resistance of our thermometer is going to be at 100 degrees C. Now you guys can use so essentially what the textbook does, it breaks up basically one formula into 2 different steps, where you just calculate the change in resistance. That's essentially the change in temperature times the thermistor resistance at 20 degrees C multiplied by the temperature coefficient, and that will then give you a change in resistance of 80 ohms, and then you just add it to the nominal resistance of your thermometer, and that then gives you a total of 1080 ohms. Or you could have even done this, if I remember correctly, yeah, you can actually use this formula as well. That will also work. Because essentially that's just the textbook basically just splits everything as such. So yeah, so there you have your initial temperature, so your temperature at 20 degrees C, and then your final resistance at 100 degrees C. Right, so then your change in temperature, that would just be 100 minus 20, which is 80. So yeah, so pretty straightforward, not too difficult. Yeah, and then you can pretty much just plug everything into your equation. And yeah, so the voltage that you're going to measure across your detector bridge is then, in this case, 57.7 millivolts. Now that is quite a small voltage. You can't really do anything with that small voltage unless you amplify it. So in the second part of the question here, we are tasked with calculating the feedback resistor value if our output, so if the output of our detector bridge is connected to a 1 to 5 volt system, and the metering resistor given to us is also 1 kilo ohms. So the input resistance to our amplifier and the output voltage must be 5 volts at 100 degrees C. Right, so we are going to go to our max value at 100 degrees C. Right, so essentially we take our, so this then is our input voltage for our amplifier. That's what we have there. So if we have our formula here for our non-inverting amplifier, then if we manipulate it, we can calculate the feedback resistance as such. Then it's just a matter of substituting all the values. Again, we want the output voltage to be 5 volts at 100 degrees C. There's our voltage drop across our detector bridge. And this is our metering resistance or input resistance to our amplifier. And that's then going to give us 85.7 kilo ohms for feedback resistance for this example. All right. So yeah, so I'll see if I can maybe do another. Yeah, so this is actually kind of two examples in one here that actually demonstrates the, how can I say, the reliability or the interaction between these two different circuits. Then you can also have attenuation. Now, what is not shown here with the attenuation is that you can have an amplification stage right about there. So that can also be, again, a non-inverting amplifier that you can have there, amplifying the voltage. Now, this circuit here is essentially used to mix voltages. So as you guys can see, if we have two signals coming in from two different sensors or two different transducers. And we typically will do this if the two signals together, it's going to either, sorry guys, so the voltage is either too high or they are going to saturate your amplifier if you just apply the signals to your amplifier. So these signals need to be attenuated first before we can do anything with them. Right, so essentially your output voltage here is then going to be the sum of the two attenuated voltages. So you're going to have V1 attenuated by this ratio and V2, maybe just underline V1 here also in red. And then for V2, it's then just going to be attenuated by that ratio there. So R4 to the total of R3 and R4, and V1, R2 to the total of R1 and R2. All right, and then these two voltages are essentially added together as your output. But again, like I said, you can have an amplification stage here between your final output and the attenuation circuit. So typically, I know there's an old exam question, and I think this thing, you get given all the other values, even your output voltage, but then you have to go and calculate what that amplification or that amplifier gain needs to be to get that output voltage. Right. Okay, so just want to make 100% sure here with the textbook if we don't have any exercises on that. Okay, so no attenuation circuits still in the exercises. Right, okay. But there are some other examples there that I say is a bit more tricky, so I think we'll take a look at those. Anyways, let's continue real quick. I just want to get some of these signal processing operations out of the way, and then we can go on to more examples. Okay, so then we also have linearization. So linearization is typically implemented when you have a deviation from your linear relationship, which is known as non-linearity. So yeah, so your measurements start to depart from a proportional relationship. So you don't have a linear relationship anymore between your input and output, right? So you get something that will look like this. So things that especially have how can I say linear or linearity issues would be a lot of your magnetism or rather electromagnetism based transducers due to saturation. So you can only so but the reason why I use magnetism here is because certain materials, actually all materials have a limit to how much they can be magnetized. So you can only put so much magnetism in an object, right? So then you get to a point where you can increase the flux but the flux density in the material doesn't increase any further, and you don't have any further increases in voltages or currents relating to that. Right, so that would be an example of nonlinearity. Right, so typically you then have some form of inverse nonlinear correction that you need to implement. Now, yeah, so for this subject, I don't think, yeah, the subject we really don't really go into implementation things here. In fact, the textbook does have a circuit here for that, but it looks more like a detector bridge thing. And they don't even say whether this is for linearization. So let me maybe just show you guys. That's essentially what we already had with the detector bridge. So nothing really special. So you guys, there's your graph, and then we have, yeah, so we have a Whetstone bridge or detector bridge. Yeah, to get an output proportional to the change in resistance. In fact, this would actually be a good idea to show you guys as well that, how can I put this? So for this linearization of the change in resistance, in fact, the detector bridge already does that. You actually don't really need this op amp here for that linearization. So I'm going to, this thing, I love it when this thing just jumps pages. So just to give you guys what I'm actually, or just to describe what I'm actually talking about here, if you take a look at Ohm's law, yeah, so if you do want to measure resistance, for instance, this is going to give you a nonlinear relationship, right? So in fact, you're going to have an asymptote as you approach 0 amps, right? So you're going to have something that will, how can I say, you're going to get to 0 amps, but yeah, so you're going to have a graph that's going to look something like this, essentially. So as you reach 0 amps, your voltage is essentially going to get, or your resistance is essentially going to become infinite. But as you reach, yeah, so, but your resistance will be really, really low here on, yeah, so as you guys can see, it's going to be a non-linear relationship. Now, in order to linearize that, you can use a Whetstone bridge. So essentially, that's actually why the Whetstone bridge, that's actually why we use detector bridges and not just plainly resistors to do voltage detection, because of this little problem. Okay, so I think I skipped now. Then we have offsetting. Yeah, so offsetting is something that we just want to see if I can get back to this part in the textbook that we need to be at. Yeah, so you're basically going to use it in one of three scenarios. So for a start, if you have a measurement of very small changes over a large initial amount, essentially what that means, I'm going to try and show this here as well. So if you have, for instance, let's say a very large DC component to your signal, but you have just small changes around that DC component. Now, I hope you guys can see that the DC component doesn't really carry any information for us. But the changes, that is what we want to measure. Now, if you were to take the signal and just chuck it into an amplifier, there's the possibility that you might saturate your amplifier and thus lose all that information on your output. All right, so that's one place where you want to use offsetting. So you essentially, what you want to do is you want to shift the signal down to 0 volts or to a lower voltage, just so that you can actually amplify that signal properly. Then measurements employing a device that has an absolute scale, right? So degree C versus Kelvin. Again, you're coming into a similar problem as what we had here. So Kelvin is only positive values. There's no negative values. So you can run into a bit of a problem there. Again, with saturation. So you could be measuring temperatures in Kelvin, but again, like I said, only positive values. Now, if you have big fluctuations, yeah, so ideally you would want to move this signal a little bit more towards the 0 line as your average, and that will give you a bit better control on how you're going to do your amplification. So yeah, so that one was a bit drastically drawn there, but I think that would be fine. And then lastly, we would introduce an offset where your minimum value is above 0. So for instance, if you're converting a 0 to 10 volt signal to maybe a 4 to 20 milliamp signal, now there's no way that you're going to amplify that 0 volts to correspond with that 4 milliamps there without any offsetting, right? So that 0 is going to make everything 0 every time. It's the same thing if you were to go, let's say, from even from one, let's say from a 0 to 5 volt system to a 1 to 10 volt system, then you, of course you will again need some offsetting there to achieve that 1 volt on the output from a 0 volt input. Right, so that's essentially where your offsetting is used. In fact, did I skip something here? And then we just have general interfacing as well. So with interfacing, so the term, so in the textbook, the term is mainly used to refer to interfacing, a 1 to 5 volt system to a 4 to 20 milliamp system, or the other way around. Now, so I essentially jumped the gun here to this point, but if you do look at what interfacing is, so interfacing, so interfacing circuit can either be described as a driver or a receiver. Now, a receiver would be a circuit that accepts inputs and then will provide a high input impedance to your output. Or actually, no, it will provide a high input impedance to your input, and your input signal is usually from a driver. Yeah, so usually you will have a driver inputting into a receiver. But yeah, any case, so your receiver is essentially to minimize the loading of your input signal, while a driver circuit, on the other hand, gives you an output signal at a voltage or a current level that's then ideally suited to your load, right? So for instance, how can I maybe put this? So if you had an inverter, for instance, so an inverter actually needs some form of driver circuit so that the switching of the transistors happen in the correct sequence and that your load is correctly powered. So there's an example of a driver circuit. Another one would be, so basically, and also something that can just switch your motor on and off. Going to need a driver circuit for that as well. So you can't just directly connect your control electronics to your motor. You're going to have some interface in between that. Like, things like, I think a very good example would be things like your variable speed drives for motors, both DC and AC machines. All right, so here we're actually going to take a look at a few examples again. I just want to see, do I keep skipping stuff here? Yeah. So the first interfacing circuit that we'll take a look at is the voltage to current interfacing circuit. Now there is an example here in the slides, but I will do an exercise from the textbook as well for this one. So we typically then have an input. So you guys will see this looks a lot like an inverting amplifier, especially if you just look at this part here and ignore that resistor there. But essentially what we have here is an inverting amplifier. So we have a load then connected on the output of our op amp there, and in series with the load we have what we would call a dropping resistor. And that dropping resistor essentially gives us a voltage level that we can measure, or in this case a current, or rather it makes the current a voltage that we can actually measure. But anyways, so we can describe the output voltage so as you would with an inverting amplifier. So in this case, the negative because it's inverting, so it's going to be the negative of V in multiplied by the ratio of your feedback resistance to input resistance. And but if you look at, so that's basically this part of the circuit. And then if you look at the second part of the circuit here, that part, that is essentially, so essentially we have here that the output voltage is equal to the load current. So this load current here is going to flow that way. So that's essentially the load current multiplied by the dropping resistance. So now you guys can actually see, you can actually equate these two together now, which is done in the example. Because the output voltage is is both these things at the same time. And and you can then use this to go and calculate your drop-in resistance. So I think in this example, we have a 1 to 5 volt source that we need to interface with a 4 to 20 milliamp system. Right, so essentially we're pretty much just going to look at the maximum values there. So 5 volt needs to correspond to 20 milliamps. And we're told that the input and feedback resistors both, so R2 and R1 are both 50 kilo ohms. So that actually simplifies the calculation a little bit. So that actually just becomes 1. So in the example here, it is actually kind of excessive to keep those two resistors in there, but just for demonstration purposes, that is what we have here. In fact, I also believe that this should also be negative if you think about it carefully, because the output voltage here is going to be negative across that resistor. So because of the inverting amplifier. But anyways, so you can always just make that value positive because the resistor can't be negative. Right. Then you also have a current to voltage interfacing circuit, so very similar to this, just the other way around. Again, so we have our we have an input current source, and we have a voltage divider circuit here, formed by our load. So the load that causes the current there, or causes fluctuation in current. But we also put a drop-in resistor in series with that to give us an input voltage that we can make use of. So that input voltage would then obviously be proportional to the current from our current source. And so then we have a difference amplifier or differential amplifier that we use here. And and I believe so basically your output voltage is then given this formula here. And and if R1 and R2, so both these resistors are R1, and then you have R2 there and R2 there, if those resistors are all the same size, then that becomes 1. Right, cool. Then that simplifies your equation a little bit there. I was trying to remember how this is derived though. So again, so your input voltage, rather, I have this whole thing again. So V out is going to be V in. Now, because this difference amplifier has the resistors mirrored essentially, you can just use non-inverting amplifiers or an inverting amplifier's formula, but with a non-inverted output. So that will work. But V in at the same time is the same as your input current multiplied by your drop-in resistance. Right, so then you can just substitute this in there, and then you get that formula there. Right. Okay, so then there's some ideal and non-ideal characteristics for op amps. You guys should just go read through that. I'm not going to spend too much time on that. I actually just want us to take a look at some examples. I'm going to quickly just go through the summing amplifier. As you guys can see, this is essentially just an inverting amplifier. Now, they actually don't get scared, or rather don't get frightened by this kind of circuit. It's actually very easy to solve, especially if you use superposition. So essentially what you can go and do is you can ignore those two voltages and then go and calculate essentially just V1's contribution to the circuit. And then you can do a similar thing then for V2. So if you take V1 and V3 out, then you can go and calculate V2's contribution. And similar thing with for R3 as well. Just take so V2 and V1, take those out, and then you have V3. And remember, it is an inverting amplifier, so so essentially those bits of how can I say, each one's contribution is then just subtracted from one another. All right. Or just negative numbers added together. You can also view it that way. Then you also have the integrator circuit. Now, the textbook does have an exercise for a summing integrator. So summing integrator, you're just essentially adding resistors and input voltages here. So V1, V2, V3. So you're just going to have 3 sets of formulas that you have to just add together. Right, so it's actually really not that difficult. It just looks very intimidating, but I mean, you're just going to go do the, basically you can go just calculate what the output voltage is going to be for V1, for V2, and V3, and just add them all together. All right, so that's pretty much the easiest way to approach it. You can, however, if you want to solve everything in one go, but because, especially if these resistor values are all different, you might want to go just separately calculate each input voltage contribution there. So then that formula will become something like 1 over C multiplied by, then that's going to be 1 over R1 with the integration of V1 plus 1 over R2, the integration of V2, and the same with R3. Right. Cool. So it's really not that complicated. It just looks very intimidating because you have an integral there. But it's really, I'll show you guys in a second. It's really not that difficult. And then differentiator circuit. So it basically just takes your input signal, differentiate it, and the relationship between the input and output is looks like that. I don't think there are any calculations in the textbook on this. I actually checked now in the previous syllabus textbook, there were no calculations done with differentiator circuits. But I see they do practical differentiators and integrators here, which is a bit of a new one for me here. It's usually for N5, that one, but it's okay. Let's take a look at it. Just want to see if they do go into this. We also have comparators as well. We actually have that one lost in the slides. The differentiator, we have the practical differentiator here, and and it's the exact same example as what is done in N5 in any case. So we'll take a look at that as well if we have the time, but I will want to do the more difficult ones first. All right, so analog comparator. So you guys will see in the textbook there is a quite an interesting, how can I say, drawing or graph on how they explain this, the operation of this. So typically you will have a reference signal on your one terminal. Now you can swap the reference and your input, so you can have it either way, it doesn't matter. It's just going to influence what your output signal is going to look like. But as we have it here, if your input is bigger than your output, not your output, if your input is bigger than your reference signal, then your output is going to be driven to plus VCC. So it's going to be driven towards the supply voltage of your op-amp. And if your input is less than your reference, then your output is going to be driven to minus VCC. And if you connect this part to ground, however, that's going to be driven to 0 volts. Right. So I think you guys can see this is actually a very nifty way to use what is it, an op amp to digitize a signal. So if you don't really care about the analog nature of a signal, if you just want, if you just want to know when that signal is above a certain threshold, and you want another circuit to operate during that time, or you need an output to switch on or off, then you have, so this circuit can actually help you with that. Very simple, but very effective as well. Right, but it's something to keep in mind is that your amplifier is driven to saturation with this. If you use it in this manner. I'm just going to quickly jump to the textbook here on this one. Just want to show you guys the graph that's used here. Right, so essentially what we're given here, I just want to see which is our reference signal here. So you can actually, your reference signal doesn't necessarily have to be a DC signal. It can be something like a sine wave, for instance. I believe here the reference signal here is your sine wave. Now you guys will see every time that that the V1 signal is bigger than the V2 signal here, then you're going to get your output driven high. In fact, there is a bit of a mistake here, is that in fact your signal should be driven towards minus VCC in the time that we want. In fact, let me maybe do this, because like I said, there's a mistake actually here. I'll show you guys real quick what I mean with that. If they wanted to, whoever wrote the textbook, if they want the output here to be as it's shown here, the amplifier needs to only be supplied plus VCC and ground. I'll show you guys now in a second what I mean with that. This thing works with me, which it's not doing now at the moment. Okay, let's do this. Okay, I'm just going to quickly share to the whiteboard and then yes, I didn't open my whiteboard. Okay, give me a few seconds. Okay, so basically the mistake that was made here, should have actually copied the circuit width. Because the circuit is connected, so because the op amp is also minus VCC, this should actually go down to, should actually do this as well. All right, then when it goes lower here, so now this part is, so this should actually then, beyond this, so this should actually stay up there till there, and do this. In fact, then it's going to go straight over like that again. Right, so that's actually what it should look like. All right, so there is a bit of a mistake in the textbooks drawing of this. But anyways, let's take a look at a few examples. In fact, I want us to quickly take a look at the summing integrator, as that one is, like I said, it looks intimidating, but it's actually not that bad. There is an example in the textbook on this one, but I'm going to take a look at the example. I'll take a look at an exercise, then you guys can take a look at it as well. So I think it's in, what's this exercise number? I think it's exercise 2.1, number 31, right? That's on page 98. Those of you making use of a hard copy of the textbook, or page 103 according to Prelego. Right. Okay. So so basically we're giving the following data regarding a summing integrator. So our first input resistance is 1 kilo ohms, second is 100 kilo ohms, and the third is 4 kilo ohms, with our corresponding input voltages at 4 volts, 2 volts, and 6 volts. Right, and we're given the feedback capacitor as 0.5 microfarad or 500 nanofarad. Right, so basically what that circuit is going to look like is something like this. Let's see, let's just draw this. And you have your feedback capacitor. So your circuit is going to look, yeah, like I said, your circuit is going to look something more or less like this. So R2, and then we have R3. V1, V2, V3. Right, so that's what your circuit is going to look like, and this here is then going to go to ground. Right. Okay, so we need to go calculate what the output voltage is going to be. We want the output voltage after 100 microseconds. So you guys will see that you're going to get an equation here for the output voltage, because we're going to integrate in terms of time the whole time. Right, so what your formula is going to look like. So I'm immediately just going to do this. So the output voltage is going to be minus 1 over C multiplied by 1 over, you can actually, you know what, let's make this easier on ourselves and do everything separate. So 1 over R1 times C, so that's going to be 1 over, what is R1 again? That's 1 kilo ohm, so that's 1 times 10 to the 3, and that's 0.5 times 10 to the minus 6. Let's see, that's going to be basically 1 divided by 0.5 multiplied by 1,000. So this is going to be 2,000, that fraction. And then we're going to have 1 over R2C. So that's going to be 1 over 100,000 multiplied by 0.5 times 10 to the minus 6. So that's going to be is it 1 divided by 50 multiplied by 1,000. That's going to be 20. And then lastly, you're going to have 1 over R3C. And that's essentially then going to be 1 over 4 times 10 to the 3 times 0.5 times 10 to the minus 6. So that is 1 divided by 2 times 1,000. That's going to be 500, that fraction. All right, so that makes just life a little bit easier for us when doing this thing. So you can actually go and write now. So if we do the integral and whatnot, so we actually simplified this formula a little bit. That's now essentially minus 2,000 integral of 0 to t. So just imagine 1 over R1C there. Then what is this going to be? V1 is 4 volts. So just fill it in like this for now. Minus 20 0 to t V2 dt minus 500 0 to t V3 dt. Okay, then going to be minus 2,000 integral from 0 to t. V1 we have here is 4 volts, minus 20, 0 to t. V2 here is 2 volts. I'll write the volts just here to dt, minus 500, integral from 0 to t. That's going to be 6 volts. Right, so that is then minus 2000 multiplied by 4t minus 20, 2t minus 500, 6t. And that is then, so 2000 times 4, that's, is it 8000? That's minus 8000 t minus, that is then 20 times 2 is 40 t, 500 times 6, that's going to be 3000 t then. And then if we add them all together, so 8000 plus 3000, that's going to give you 11,000. So that's minus 11,000. That's 11040 t. Right, so there's your output voltage. So that is your 31.1 answer. And then they want the output voltage after 100 microseconds. So that's quite easy. So 100 microseconds. So that's just going to be then minus 11,040 multiplied by 100 times 10 to the minus 6. Let's quickly calculate this. So that's 11,040 multiplied by 100 divided by a million. And that's going to give you 1.104 volts at that time instance. And then they want the output voltage rate of change at t equals 0.1 milliseconds. Now, this is actually the same time. Now, rate of change is if you go and differentiate this. So if you take your 11,040 volts here, so what is it, 31.3. This is then going to be, so if you differentiate this, so the problem is your rate of change is going to stay the same, doesn't matter what your time is. So if you differentiate this, this is then just going to be minus 11,040, but not volts, but volts per second. Right. Oh yeah, and this, I forgot, that is actually a negative value. This minus 1.04, so don't forget that. Cool, any questions? So just remember with like the summing integrator here, if you get this thing, you don't have a formula for it. So you essentially will have to kind of build the formula for it, but it works the same as a summing amplifier. I mean, the summing amplifier, if you have 3 inputs, it's essentially just 3, you call it 3 inverting amplifiers that you just add together. It's the same that we did here. It's just basically 3 integrators that we added together. There are, however, I quickly just go to the textbook on this. So I did see now here a few differences from previous syllabus. Oh, yes, let me just maybe start off from here. There's some calculation here, but I mean, this is essentially the same formula as what you have with the detector bridge. So I don't know why. Okay, I don't know why they. Yes, I'm going to lose it with this per Lego. I don't know why it does this, but in any case, so it's essentially the same formula as your detector bridge because, well, lo and behold, it is a detector bridge. Right, so not really anything different there. Now, if we go take a look at, so here's a summing amplifier with just 2 inputs, but you can add, like I showed you guys, you can add a third. So pretty straightforward to work with this. Then There's one with 3 inputs. Again, quite straightforward. Quite a few examples in the textbook as well. Now this is an interesting one. So again, what is this? Okay, yeah, so this is a supposedly a non-inverting amplifier. Only problem I have here is your feedback resistance isn't right here. To add two voltages together. Now, this is a very convoluted way to do it, though. You don't have to actually, but in any case. Okay. So yeah, so as you guys can see here, the formula is a little bit different. I personally wouldn't do a non-inverting summing amplifier like this in practice. I mean, I don't know why, because now you have positive feedback here, which is a big no-no on an amplifier. So yeah, so I don't know why they went with this circuit implementation, but okay. But there's the formula for that summing circuit. Again with this. I'm starting to think this might be a mistake that the author made. Anyways, there we go. There's the formula for this one. Operational amplifier operating in the non-inverting mode. Yes, this is a bit of a problem. But yeah, but that's what you guys need to know. It's in the syllabus. And yeah, and then next week we're going to take a look at ultrasonic theory. All right, guys. If you don't have any further questions, have a good evening, and I'll see you guys next week. Cheers.